Oh, that was in force. Okay. Okay. What is the CGS unit of Coulomb? This electric charge. CGS unit.
State electron.
Are you talking to yourself or telling me?
Is 1
CGS
coulomb.
unit of electric charge.
It's coulomb, right?
Coulomb is SI unit. I'm talking about the CGS unit.
Don't know, sir.
The CGS unit is stat Coulomb. I told in the last one, right? The CGS unit of electric charge is stat Coulomb. Okay.
Yeah.
1 Coulomb is equals to how many millicoulomb?
10 to the power 3.
10 to the power 3. 1 Coulomb is equals to how many microcoulomb?
10 to the power 6.
10 to the power 6. Okay. Now tell me, 1 microcoulomb is equals to how many coulomb?
10 to the power minus 3.
Yes. And similarly, 1 microcoulomb is equals to 10 to the power minus 6 coulomb. Easy, right? Nothing difficult.
Yeah. Yeah.
Okay. Okay. When there is loss of electron, what charge appears on the body?
When there is loss of electron, it is positive charge.
And when there is gain of electron?
It is negative charge.
Okay. If I give you a hypothetical condition that I have a body who has 2 electron and 2 proton. I give this body 3 electron, then plus 3 electron, then I removed 1 proton, and then okay, let's not talk about proton, let's talk about electron only. Then I removed 2 electron, then I removed 1 electron. What is the charge on the body?
It will be neutral.
Neutral. Because I gave 3 and then I took 3. So it is equal to 3 minus 3 is equal to 0. So it will be the same condition. That is neutral, not uncharged. Uncharged is different, neutral is different. This is neutral. Quantization of charge. What was the formula? Q is equals to?
N by E.
N into E. What values of N can I put in this formula? Can I put minus 3?
No.
No. What values can I put in this N?
Whole numbers above 0.
Okay. Quantization. It was the minimum packet of charge. This all we have seen. Okay, then let's moving forward. We were to talk about this is done. Okay, let's talk about conductors. What are conductors? You must be having an idea what are conductors. Tell me.
Objects which have free electrons and are able to conduct electricity.
They have free electrons and
Are able to conduct electricity.
they're able to conduct electricity. Very good. So write the heading conductors. In this, right, substances which have free electrons and allow electric current to flow through it are called conductors. Example, metals.
Yes.
Written.
Yeah.
Substances which have free electrons and allow electric current to flow through it are called conductors. Now, okay, I have
Yeah.
said two things here. Number one, I said which have free electrons, which have free electrons. Okay. Second thing is that they allow electric current to flow through it. How are both the points linked? Can you think? How does having free
Because
electrons
only
will allow you to
because only
conduct?
because only if they are free electrons, electric current can flow.
Hmm. Electrons are bound in that case. So you can say if the electrons are bound in that case, the substance cannot conduct electricity, right?
Yeah.
Hmm. Why are metals a good conductor? Because metals have a lot of free electrons, right? And as
Yeah.
soon as we conduct electricity, the electrons rush very fast and it's a very good conductor of electricity.
Mm.
Can you tell me which metal is the best conductor of electricity?
Silver,
Why?
because it has so many free electrons.
Right, silver is the, right this point. Silver is the best conductor of electricity because, right the again, because because its atomic structure allows highly mobile electron. Because its atomic structure allows for highly mobile electrons. Because its atomic structure allows for highly mobile electrons to flow, highly mobile electrons to flow
Yeah.
with least resistance, with least resistance. Resistance, we'll see what is resistance, right?
Uh,
But the point is that since its atomic structure is, it is that way, it is so small that the flow of electric current is very much in silver. What is the second best conductor metal of electricity?
copper.
Copper, yes. Write it down. Copper is the second best conductor of electricity.
Okay.
Hmm. Give me the reason. We use copper in wires, right? The wires that we
Yeah.
have in a copper is there instead of silver. Why are we using copper if silver is the best conductor of electricity?
Silver is expensive.
Yeah, because silver is expensive. Because silver is not, we say it's not economical. We talk about economy, right? So it becomes very expensive for us to use because silver is not economical. Because it's expensive. Okay. Now talking about insulators. Right, substances which do not allow electric current to flow through it are called insulators. Substances which don't allow electric current to flow through it are called insulators. Example would be non-metals,
Except
plastic,
graphite.
wood, right?
Yeah.
Hmm. These are all examples of insulator. And now we talked about that something which allows electric current to flow through it and something which does not allow electric current to flow through it. It is basically depending on what presence of free electron. So presence of free electron is very important for a material to become a conductor of electricity or to become a non-conductor of electricity. Okay? There is one more term called semiconductor. Heard of this term? Put the heading
Yeah.
semiconductor. If you written the example, write the examples.
Right. So plastic and
Plastic, wood is all insulator. Does plastic conduct electricity? No, right?
no.
That is why you must have seen. This is also an application-based question. That why we use wooden handles or plastic handles or PVC handles in utensils, right? Because utensils can because they are made of metals. So metals can conduct electricity and heat both, but wood and plastic cannot. Yeah, that is why we
So
use.
for conduction of heat also we need free electrons.
Yeah, definitely. What will happen if heat is provided? Then electrons will get excited. What does heat do? If you have given heat, so heat is a form of energy, right? So this
Yeah.
energy is transferred to electrons. And when these electrons gain the energy, they start moving.
Then why plastics melt?
Plastic melts because there are no free electrons. And when you give it a temperature more than it can withstand, so its molecules start to collapse and it melts.
Then why wood doesn't?
Wood burns because it has its property that wood burns. Plastic will also burn, but it melts. That is the property of the material.
Oh.
Semiconductor. Put up the heading. Semiconductor are the materials whose conductivity, sorry, whose electrical conductivity is between conductors and semiconductor. Sorry, conductor and insulators. Conductors and insulators. Materials whose electrical conductivity is between conductors and insulator. So like if we talk about the conductivity, so which is very high for, let's suppose I'm taking this line, this is for conductors and this low line is for insulators. The semiconductor will lie between them. That is why that is they have a name, semiconductors. Semi means partial or half, right? Now, how semiconductors are made, why they have less conductivity. This is all you will learn in class 12th. That is not in your syllabus. Example,
Example.
example, I don't think you need to write. You can write gallium. Gallium is a metal which is semiconductor. Written.
Yes.
Now we'll study about electric potential. Put the heading electric potential.
Yes, sir.
Right, electric potential at a point. Electric potential at a point in an electric field is defined as electric potential at a point in an electric field is defined as. I mean, have you understood? First, you tell me, is this line clear? Whatever we have written so far. Okay. Electric this is not we are defining, we're not defining electric potential. We are just framing that what all comes with electric potential. See, electric potential we are talking about. Electric potential will be at a point. Electric potential is always measured at a point, right? So
Yeah.
electric potential at a point, which means that whatever point you are talking about, at that point, what is electric potential? So electric potential at a point. Now, potential is always in an electric field. Without electric field, we don't talk about electric potential. So then the definition becomes electric potential at a point in an electric field is defined as, understood the language?
Yeah.
Is defined
Yeah.
as the work done. First you understand, then you write. Is defined as a work done in moving a unit positive charge from infinity to that point. Write it down. Written. Written.
Yeah. Yeah, sir.
I'm asking, have you written?
Yes, sir.
Okay. So what is electric potential? First line I think is clear. Electric potential at a point, we will be talking about a point where you define
Yeah.
electric potential in an electric field. Electric field will be there. Now, if you are in a, for example, when you are in electric field, so when you are in an electric field, so you feel an electric force. So electric field makes us feel what kind of force?
Electric force.
Electric force. If you are in a magnetic field, what kind of force will you feel?
Magnetic force.
Magnetic force, very good. If you are in a gravitational field, what kind of force you will experience?
Gravitational force.
Gravitational force. Gravitational field means on the planet Earth, we have a gravitational field, right? So we feel a gravitational force.
Yeah.
Similarly, in this electric field, you will feel an electric force. So you will feel an electric force here. Okay. So which means electric force is there because of electric field. Now, in this electric field, where electric force is there, and you have to define an electric potential. So electric potential at that particular point in an electric field is defined as the work done in moving a unit. Okay, now let's first understand. First, let's understand through diagram. Then we'll go on the definition. Okay, so let's suppose this is a an electric field. This red line, what I have drawn as circle, this is an electric field. Because of this electric field, there is electric force. Now I have this positive charge. I don't know the location of this positive charge. So what I'm assuming is that this electric charge is at infinity. Okay, this electric charge is at infinity. Infinity, you know?
Yeah.
Now I want to bring uh, this unit positive charge from infinity to a point in my electric field.
Okay.
So what
So
I
you're
am
bringing positive,
huh?
bringing a positive charge
Yeah,
towards a positive charge.
I'm bringing a unit positive, and that is I'm defining an electric field. Now this is a unit positive charge. Now you must have asked that why am I not taking a negative charge? That is how it has been derived by the scientist, right? We have to study it that way. What they did is that they define electric potential as there is a positive charge at infinity, and I want to bring this charge from infinity to a point. Let's take any point to a point in this electric field. Now, whatever, now if I do something, um, okay, so that would be a work done, right?
Yeah.
This is basically a work what I'm doing. I'm taking this infinite positive charge from infinity, bringing to a point in electric field. So this is basically a work done. So that work done which I am doing, the work which I am doing in moving a unit positive charge, this is unit positive charge from infinity to that point. This is defined as electric potential. Understood?
Yes.
So let's see the definition again. Electric potential at a point in an electric field is defined as the work done, that the work you do in moving or bringing a unit positive charge from infinity to that particular point.
So
Understood?
electric potential is measured in joules.
Sorry,
Electric potential is measured in joules.
is measured in joules. This is what you're saying.
Yeah.
This we'll see. Abhi, when we'll be deriving the formula, then we'll see that how it is, what value do we take for it. It would not be joule because this is not work. This is work to bring a unit positive charge, which we'll see. First, you write this.
The answer.
Name this point as A. Mark this point at A. We're just talking about point A, that I'm bringing this charge from infinity to that point. Write one star point. Electric potential. I am writing EP. You don't write EP. You write full electric potential. Okay. Electric potential is a scalar quantity.
What is the scalar quantity, sir?
What are you asking? What is scalar quantity?
Yes. Yeah.
Yeah, we are not students. Vector quantity, scalar quantity.
No,
Okay.
I don't remember.
Okay, let's see. Let's suppose if I talk about force, this is a wall, right? And this is a floor. And here one box is kept. If I zoom in to
Yes.
show you. This is a wall, and here one box is kept, and this is the floor. Now, if I say that the force required to move the box, uh, let's make the box a little away. Okay. if I say that the force required to move the box is 10 Newton, let's suppose. Okay. So, which means that how much force do you need to move the box?
10 Newton.
10 Newton. But you should be applying the force in a specific direction. If you push the box like this, what will happen in the box? Will the box
The
move?
box. No.
No. But you are applying 10 force. I told you that you need 10 Newton of force to move the box. You are applying 10 Newton of force, but the box is not moving. Why? Because you are applying force in a wrong direction.
Yes.
Which means you need to apply force, but in a right direction. So which means if you apply force here, the box will slightly move and stick to the wall, which means the box will move, right? Which means you are applying force in a right direction. If you come and stand here and you push the box, then the box will move here. So which means you are requiring you are using 10 Newton of force, but you are now doing it in a right direction. So the box is moving. So force is a quantity in which magnitude is required with direction.
Yeah.
10 Newton was magnitude, and the direction left, right, up, down was the direction. Which means force is what kind of quantity? Vector quantity. What kind of quantity is force?
Vector quantity.
In vector quantity, both magnitude and direction are required. Repeat, what is vector quantity?
When both magnitude and direction are required, it is called vector.
Second. In vector quantity, both magnitude and direction are required, and on the other side is a scalar quantity. Scalar quantity is the one in which only magnitude is required. We don't talk about direction here. For example, mass. Let's suppose this is a weighing scale, right? You stand on it, you will measure, let's suppose 50 kg. If you lay down on it, then also you will 50 kg. If you put your heads up and stand like this, then also you will 50 kg. So you are changing the direction. But is the mass changing? No, right? Which means there is nothing to do with direction. Only magnitude is required. That is why mass is a scalar quantity. Understood? What are scalar and vector quantities?
Scalar doesn't need direction, while
In
vector.
scalar, we talk about only magnitude, but in vector quantity, we talk about magnitude as well as direction. Okay? So we were talking about electric potential. What have you written?
Electric potential is a scalar quantity.
Right? The SI unit of electric potential is, right? SI unit of electric potential volt defined by V.
Okay, sir.
SI unit of charge.
What?
SI unit of charge. I'm asking you.
Is a unit of charge is current.
An SI unit of electric potential.
What?
Volt. SI unit of time.
Seconds.
Now write potential difference. We have seen what electric potential is. Now write potential difference. Potential difference.
Okay,
The
sir.
potential difference between Hello, hello, Umair, am I audible?
Yeah,
What happened?
the connection went off.
Hmm?
The connection went off, sir.
My screen is visible?
No, sir.
Not visible?
Yeah, it's visible.
Hmm. We were talking about potential difference. First, you write the definition of potential difference. Write the definition. Written.
No, sir. Yes, sir.
Hmm. So what was potential, electric potential? So electric potential, what we were doing, we were talking about a point in an electric field. And at that particular point, what you are doing, you are bringing a unit positive charge from infinity to that point. Clear?
Yeah,
Now in potential difference, we are not talking about infinity. So what we're talking about, the potential difference is between 2 points. We're talking about 2 points. We have taken 2 points. The potential difference between 2 points,
2 points
let's
in the electric field.
A and B. We have taken 2 points. Now, what we are
Yeah,
doing is I am bringing unit positive charge from A, and then I bring the positive charge from B. So it's between the 2 points. That between the 2 points, what I do is the work done in moving unit charge from one point to another. In this electric field, if I mark 2 points A and B, so what will be the work done if I move a charge from a given point to another given point? What work done will be there if I move that charge between the two given points? Read the statement.
it will be electric potential of A minus electric potential of B.
Yeah, you can say that that way also. Like, let's suppose A we are bringing from infinity, B from infinity. So we take electric potential at A from infinity minus electric potential of B from infinity. And instead of doing this much, we have concise and we have written electric potential from A into B. Right? Now let's see the formula. The potential, what was the SI unit of electric potential?
Volt.
Huh?
Volt.
Volt. Okay. So now the formula is V is equals to W by Q. V is equal to W by Q, where V is electric potential or potential difference, right? V is you can write it all in the formula only. Like V is the electric potential or potential difference. What is W? Is the work done, and Q is the charge. So if when we talk about electric potential, then we will say V is equals to W upon Q. When I talk about potential difference, then what I'll say? I'll say V1 minus V2 is equal to W by Q. Why? Because I'm talking about electric potential difference. In potential difference, when I talk about two fixed points. See, here also I would have said V minus 0 is equal to W upon Q, because this 0 defines infinity. So which needs not to write. So I only write V. But here I have that second fixed point. So I write V1 minus V2 is equals to W upon Q. This is we write when we talk about potential difference. And this is we write when we talk about electric potential. Understood?
No.
If I say, let's suppose in this case, I talk about this formula about potential difference. If I am going to find potential difference, what formula will I use?
V is equal to W by Q.
V1 minus V2 is equal to W upon Q, right? Okay.
Why V minus V2, sir? V2, sir?
What?
Why V1 minus V2?
See, that is what I'm saying. That is what I wanted to explain for writing this formula by V1 minus V2. So what we do is whatever, so we can also write it as V big minus V small, which means that we always subtract which means that V1 is greater than V2. Simple. We subtract the bigger one from the smaller one from the bigger one, right? Which V1 minus V2 definitely means V1 is greater than V2. And this is for electric potential difference. Okay, so here we can say that what is the SI unit of work? It is joule. So we can say that we can also say that 1 volt of electric potential is equals to the work done in moving 1 joule of work done in moving 1 coulomb of charge, right? The SI unit of volt was of electric potential was volt, of work done was joule, of charge was coulomb. So we can say that 1 volt is that charge which is required to move a charge of the work done of 1 joule required in moving a charge of 1 coulomb. Understood? Write it down also.
Sir, why can't we write V1 minus V2 as V?
V1 minus V2 as?
V.
You can write it as V also, but to define when you have given two, what is this potential difference? Which means V1 will be given, V2 will be given. So why will you write it as V? You will do V1 minus V2, na? If you write V only, then will you be able to find I give you two potential. If I say in a question, first potential is 110, other potential is 120. What will you write as V? 110 or 120?
V2 minus V1.
Why you are doing V1 minus V2? Because you can put anyone. That is why we are doing V1 minus V2. Because we have two potentials. That becomes V, that is a different thing, but we have to write V1 minus V2. Because that is potential difference between two given fixed points. Write all this. Right, V is equal to this also, right? V1 minus V2 so W by Q. Right, V1 is greater than V2. This also, right? 1 volt is equals to, in this also write the statement 1 volt of electric potential is the work is 1 joule of work done in moving 1 coulomb of charge. Which means if you move a charge of 1 coulomb and the voltage and the work done that you did in moving that 1 coulomb of charge, that work done comes out to be 1 joule. So the potential will be coming out as 1 volt. Written.
Yes, sir.
Make a star point and write. Electric potential is also called as voltage. Electric potential is also called voltage.
Volt and voltage is the same.
Is
Volt and voltage is the same.
voltage and voltage.
Volt and voltage are the same.
Yeah, it's same. You say volt, you say voltage. Same. But we basically defined, we use the term volt as a SI unit and we write volt, and the electric potential we also called as voltage. If I say that, I don't say, like if I say that how much voltage is coming in the circuit. So I say 5 volt of voltage is coming. You have seen rarely people saying 5 voltage of volt is coming. So volt is basically used for as a SI unit and voltage is used to define the electric potential. So we say that. So whatever has been told to you, use it that way. Don't use your own ways of writing things. It is
Yeah.
right. SI unit of voltage is of SI unit of potential difference or voltage is SI unit of potential difference or voltage is volt denoted by V.
Okay, sir.
Write this point. Voltmeter is used to measure the potential difference across 2 points. Voltmeter is used to measure the potential difference across 2 points. So if I ask you that which instrument or which device should I use? Like I want to measure, like I have a circuit, I give you a circuit, and you want to measure the potential difference in that circuit. Which
Yeah.
instrument will you be using?
Voltmeter.
Voltmeter, right? And the readings that voltmeter will give. Hello?
Yeah.
No, someone else is also joined. Anyways, let's continue. So you are measuring potential difference by using, like I want to measure potential difference. So for measuring potential difference, I'm using voltmeter. The value this voltmeter will be giving will be in what terms? In terms of
Volt.
volt. Yeah. So the voltmeter will tell us that the potential difference is 5 volt, 10 volt, 2 volt, or whatever. That it will be in volt, right? Now write second point, like another point. Voltmeter should have very high resistance. Voltmeter should have very high resistance. The instrument that we are using to measure the potential difference, that instrument, that is voltmeter, it should have very high resistance. Resistance, I mean, resistance we haven't studied, we'll be studying later. But do you have any idea about resistance?
Resistance is like the obstacles or something which reduce the flow of current.
Not audible, speak loudly.
It's like something which reduces the flow of current.
Kind of, we can say, yeah. So voltmeter should have very high resistance. Right, another point, voltmeter is connected. You written this point? Umer,
Yeah,
you've written this point?
yeah,
Okay. Right, voltmeter should be
should be.
connected in parallel with the battery.
Yes, sir.
Now, you must ask, this is the question I thought you would ask, that why this voltmeter should have high resistance? Why are we connecting this? Do you understand what is the meaning of connecting in parallel and series? Okay, let's suppose this is a circuit, this is a bulb, and this is a battery. Now, I want to connect voltmeter. So what I do is I connect voltmeter. What I told you. How we connect voltmeter? In what kind of connection? Parallel. Parallel. You means right? Parallel. You know the meaning of word parallel, which means if this is circuit, so we connect voltmeter like this.
Yeah.
It's called parallel. I'm connecting voltmeter in parallel. Later in the next lecture, I'll tell you that this voltmeter, it is used to measure what?
It is to measure voltage.
Voltage. And voltage is V. Now, if I
Yeah.
have to measure current is
Sir, I have
I.
a class at 6
Yes.
o'clock.
Sorry, what?
I have a class at 6 o'clock.
1 second, 1 minute, I'm leaving you. For current, is that you will be measuring current with the instrument called ammeter. And this ammeter, we'll see in the next lecture that this ammeter is connected in series.
Okay.
Okay, this I'll explain on the next lecture. That why do we connect this in parallel.